Very nice. Okay. Well, let me go to screen share then. And if I don't remember and you have some questions, let me know. I'll try and stop every now and again and ask for questions so that we have a clear um, understanding before we go too far into the talk. Oh, can you see that, Jean Caston? Did you see that, Dottie?
I did.
Good.
I did admit him.
Good. Thank you. All right. Now I'm going to minimize the images so that we can read this a little better. So called How to Drive a Nuclear Reactor, written by Colin Tucker. And you can see his hands are on the wheel, and inside is that classical image of an atom. There's a book that I was encouraged to read by the Atomic Book Club. There is such a book club, and we had an opportunity to meet a Zoom with the author, and he looks just like this, although he was a little more informal the day we met him online. Colin Tucker, he's worked in the UK nuclear industry for 30 years, mostly at the Sizewell B power station. This is on the east coast of England on the North Sea, and has quite a strong history of nuclear power. And he specializes in nuclear safety, enjoys teaching at schools about how nuclear power stations work. A friend of his is a steam-trained hobbyist who wrote a book about how to operate steam trains, and he thought he would use the same idea. And I think he's succeeded very well, because you do get a feeling of confidence and safety when you're talking with somebody who's worked in the industry for so long, and he focuses nicely on that. And it leads to this joke, you have to start a good book with a good joke. It's been said that a modern nuclear power station could be operated by one man and his dog. Now, the man would be there to feed the dog, and the dog would be there to bite the man if he touched any of the controls. This sounds a little silly, but it applies very well to both 3 Mile Island and Chernobyl. So it has some relevance. He says, this book won't teach you how to drive a reactor. That's a 2-year job, but it might give you a much better idea of what's involved in driving one. And I think, again, that he's there. Now, before we get into the text of his book, I thought it was good to look at the global situation. There are 450 reactors operating in 32 countries. Of those 450, 300 are pressurized water reactors. We're going to focus a little bit in this talk about the difference between pressurized light water reactors and boiling or non-pressurized reactors, to give you some indication of the differences and why the pressurized ones are a little more popular. About 2-to-1 ratio. 50 more are under construction worldwide, and 250 research reactors are operating in 55 countries. These are generally for testing materials or providing special isotopes for nuclear medicine. And by the way, as a radiation oncologist, I can tell you that this is something that I wasn't too excited about until recently, but they have developed some wonderful isotopes which can be used when linked with very nice targeting monoclonal antibodies to achieve dramatic results with stage 4 or advanced cancer. And so this is becoming an increasingly important source of materials for the field of nuclear medicine. It differs from radiation oncology in that fluids are injected intravenously. There's no use of a linear accelerator or solid isotopes in nuclear medicine. So it's a separate subspecialty within the field of radiology, and very important one. Moving on down here, there are 180 reactors or so powering 140 vessels, most of them military around the world. And They're also in some Russian icebreakers. We don't have any peaceful ships outside of Russia using these reactors. We used to have some, but they're in their museums now. But all told, then that comes to about 900 operational reactors worldwide, not counting small fast reactors that are used in space. In total, they provide 1/7 of the world's electricity and 1/4 of its clean electricity. Clean meaning non-fossil fuel CO2 emitting coal and gas, and worst of all, the horrible renewable energy called biofuels. Over time, they've given us over 18,000 reactor years of experience. I'm going to take a quick break here because I think the next slide gets us into some heavy duty stuff like fission. Let's take a quick break and see if there are any questions so far about this slide and the joke that preceded it. I'll wait to listen to see a link in the chat function, and I didn't see anything new there, so I'll proceed. Okay, he says, let's get started by reviewing atoms. And he starts off very basic. Atoms are small, really small. If you put 100 million of them, that's 10 to the 8th in a line, they'll only stretch 1 centimeter. Now in the image below, the neutrons are in blue and the protons are red. And the neutrons are there to keep the protons from repelling each other. There are strong forces in the nucleus of every atom. There are forces of attraction because of Newton's second law, or third law, no, second law. And there are forces of repulsion due to the charge of a proton. And they're quite strong as the atom gets larger. And so with helium, for example, you have 2 neutrons and 2 protons. As the numbers go up beyond carbon, you get more and more neutrons to protons. So that when you get up to uranium 235, there are, somebody could mute their phone, please, are 92 protons and the rest are neutrons. So that's the basis of.
Excuse me, Richard?
Yes.
I'm just going to go ahead and mute everybody before I jump off. And so if people want to speak, they just need to unmute themselves when the discussion begins.
Okay. Thank you very much.
You betcha. Bye-bye.
Bye-bye. So this is the overview. You can get into, in the next slide, nuclides. Now, nuclides are simply a list of all of the different possibilities of proton and neutron combinations. And one that we're pretty familiar with is carbon. Carbon-12 has 6 protons and 6 neutrons, but you can get these isotopes going up and down vertically. So the isotopes then are nuclides with the same number of protons. That would be 6 in the case of carbon, but differing numbers of neutrons. So if they only have 5 neutrons, that's carbon-11. If they have 6 neutrons, it's 12, and so on. And most of you have heard of carbon-14, and this is a special isotope of carbon. About 90% of carbon is carbon-12, and or 99%, I think. 1% or so is carbon-13, and 1 part per billion is carbon-14. It has a long half-life. That is, it's in nature, and it's very, very slowly decaying with a long half-life. And so you can use that for dating of carbon-containing materials. It's been useful for fossils and various other things where we want to look at the dating of it, of the carbon-containing material. So, so isotopes then, this is boron, beryllium, lithium, and going up, it's nitrogen, oxygen, and fluoride. And you can see all these isotopes. There are many more than this. Their carbon, for example, has, I think, about close to 20 different isotopes. You can put extra neutrons in them, and it happens naturally and sometimes artificially. But it really complicates the whole idea of, I guess you could think of Mendeleev's table when you put in these all these isotopes as well as the common ones that make up 90% of the universe. And it's relevant to what we're going to say now about uranium. You've heard that 238 is the natural state of uranium when we mine it, and that less than 1%, about 0.7% of the uranium 238 with lots of neutrons to make it more stable, about less than, as I say, less than 1% is 235 with 3 fewer neutrons. So it's said to be fissile or unstable. And when it captures a neutron, the 235 releases energy and splits or fissions into 2 smaller nuclei. You can see it in the fission process here. This was described originally by Lise Meitner in 1939. And she likens it to water. We do now, I should say. The author likens it to a drop of water in space. If you've seen people fooling with water in the International Space Station, they can part in half by fiddling around with them and getting them to fission. And getting back to Lise, she likened it to the biological phenomena of fission known for bacteria and fungi and various other primitive organisms to split in this manner. And so she applied it to physics. But this was a hard idea to imagine back in 1935. It took several other people could have, including Fermi in Italy, could have thought of it. But she thought of it first. Was never given the Nobel Prize as she rightly deserved, but she does have an atom named after her, meitnerium. So she did get some recognition later on. So this is just a footnote in history, but this is in the book. I've enlarged on it a little bit. Lise Meitner in 38 with Otto Hahn. She was originally from Austria and moved to Sweden because she's Jewish, and all her colleagues warned her to get out of Austria as fast as she could. And but she gave the ideas to Otto Hahn, and he continued to work on bombarding uranium with neutrons, and they did show fission products such as barium was one that they focused on. Now, Fermi was in Italy at that time, but his wife was Jewish, and so he and his wife rapidly, when Hitler took over and started the Kristallnacht happened, I believe, in early 1939, and Enrico moved to Chicago. And as soon as he got there, money became available, and a letter, as you know, was written to Roosevelt, and money was approved to the Manhattan Project to move right ahead, because everybody knew, the physicists who've been talking about this and the whole idea of the evolution of the atom and its structure, the physicists in Europe right away and in the States rapidly recognized that this was an enormous source of energy. And because we were at war, unfortunately, a lot of the early work was done with the thought of war. In fact, nobody thought of anything but the bomb. People were terrified that Weinberg, I think his name was, Heisenberg in Germany was working under Hitler's direction. And we still don't know to this day if he intentionally did things incorrectly. He had the right idea, but he didn't build a large enough graphite pile. And so they never got very far, but we didn't know that when we were terrified, all of the workers here at the University of Chicago, that the Germans would beat us to build a bomb. So anyway, Fermi built this pile, sort of a drawing here, a sketch of these graphite blocks, and he embedded uranium oxide and uranium metal into these blocks of graphite. And you have to have a large number of them in order to get a stable chain reaction. We'll talk about the chain reaction in a minute, but I just draw your attention to this little stick. It's an important function. This little stick here, if you can see my arrow, that's a cadmium coated stick of wood coming out of the pile. And when that's inserted, it slows things down because it rapidly gobbles up neutrons in the cadmium. And if you pull it out, that inhibitor is removed, and you can go ahead and try and get a chain reaction. Any comments, questions about that? We'll go ahead to this slide of the fission chain reaction. Fission releases enormous amounts of energy. You know, familiar with Einstein's equation, energy equals mass. That would be the difference in mass between one atom here and the two atoms. And that difference in mass times the square of the velocity of light will give you an indication. And that happens in a picosecond, a very short period of time. And as well as 2 or 3 neutrons. It comes out in the average 2.5, but it could be a 50% chance, I guess, of it being 3 or 2 neutrons being emitted. Those have a lot of energy, but they're moderated if this takes place in water, particularly light water or normal water. And so they're moderated and slowed down by a huge factor so that when they hit another atom, that will carry on. And so this idea of having the neutrons and the whole thing in water led to the use of the light water reactor for having a continuous chain reaction. They wanted to have a chain reaction because, and we'll talk a bit about that later, they needed plutonium for making plutonium bombs. But let's get back to the design of the reactor. First of all, we have to think of you can very well imagine whether you're driving a car or a truck, you have a tachometer sometimes in a car, particularly a sports car. So you want to know if the number of fissions taking place per second is going up or down or staying the same. And so just like you would in terms of a revolutions per minute in an automobile. And so you have to think of the number of neutrons in one generation and divide that by the number that were present in the previous generation. In other words, going back to the previous slide, the number of neutrons generated here divided by the number of neutrons generated here. And that gives you an idea of how fast the reactor is operating. If they're the same, and then the answer is 1, or K as they call it. And when that ratio K is greater than 1, then the number of neutrons in the reactor is rising, and so is the reactor power. Just a little point that how is the uranium housed? This is called the fuel in a pin, and there's a spring compressing these little pellets. They're 10 millimeters in diameter by 10 millimeters in height. You can see a tiny little gap between them. They're biconcave little barrel-shaped pellets, and that gives some space for the heat energy to come out and be passed through the walls. This is called zircaloy cladding. It's an alloy of zirconium, which tolerates this sort of thing reasonably well. This is a space indicating that these are long and thin. I'll show you a picture of that in a minute, and the little base at the bottom. So these then are these tiny pellets in a tall cylinder is considered the most efficient way by the physicists to allow the heat generated to be passed along into a steam turbine. And here is the assembly. Again, we have this wavy line indicating that it's much longer than this. These are guide tubes to make sure that everything is lined up properly. The fuel pins in their full length are here in purple, and this is just a hold down spring at the top. So this is sort of a skeleton. It holds 264 individual fuel pins. Most of the pins are arranged vertically in this system and in most systems, but Canada is the exception. In Canada, they didn't have large enough materials to make these reactors, and so they put them in hoop-like reactors welded together, and these are horizontal and have been ever since. And they have the Canadian deuterium uranium reactors. We'll talk about those a little bit later, but it's a can-do, and they use heavy water instead of light water, or deuterium deuterated water. We'll talk a little bit more about that later, but that's the exception to the more common light water reactors that you see here. There are control rods. These are avid neutron absorbers. Instead of just using cadmium, they use silver, indium, and cadmium alloy. And these are also inserted at various intervals. So these patterns are worked out so that you don't have the uranium pins everywhere. You have an interspersing of these control rods, and they can be raised and lowered out to control very effectively the whole system. The assembly is long, heavy, and expensive, and I'll indicate that in the next slide. They're 4 meters long. This is a photograph of them being loaded into a reactor. And this is the whole length of the thing and going down into the core. They're over 600 kilograms in weight, and they're about 7/10 of $1 million by the time you take into account the cost of all the materials, the zircaloy, and the pellets. Any questions at this point? Okay, we're going to talk about why nuclear fission is so special. There are 2 big points to make. The second one being the fission products. But the most important point is that it's a very dense energy source. We'll talk about that through this little brief anatomy of the reactor here, but there's much more to it. We'll start with this. These are the control rod lowering mechanisms here that I talked about. These cadmium containing things that go down to cool, slow down the reaction in case it's getting too intense. And they're very effective at that. The water enters here at a high temperature, but its temperature is raised even more as it comes down and passes through these very hot fuel rods. And then it comes out here. There's a membrane across here, so these can be lowered down through that membrane. And these come out as hotter by about 35 degrees. And this is one just being installed. So you see it's on a bracket and it's about to be tipped up in its vertical location, but you can get an idea of the source. And these connectors here are related to the input and output. There are often 8 of them. Sometimes they have 4 units to cool and transfer the steam, the hot energy to make steam come out of these ports. So that you'd see these input and output ports ×4 often. We'll talk about that a bit later. So just looking at the energy density, consider a pressurized water reactor, and that's what we're talking about here most of the time, that generates 1,200 megawatts of electricity. And by the way, they have about 3,500 megawatts of heat energy. And so the conversion of heat to electricity works out in most systems, whether you're dealing with a coal plant, a gas plant, or a nuclear plant, with about a 33% or so efficiency. Hard to get it higher than that. But it's equivalent to 40 loaded B-74 aircraft taking off simultaneously. If you're thinking of the amount of heat energy that's coming out of those aircraft, 40 of them, each with quite a number of jets. Or you could think of it as 1,000 large wind generators operating at about 30% capacity factor. Or you could think of it as a million tea kettles coming to a boil in less than 4 seconds. I think that's about the easiest thing to imagine, those of you who boil tea. The annual fuel supply is another interesting comparison of energy density. 25 tons of uranium are equivalent to 2 million tons of coal. And that uranium comes about every 1.5 to 2 years for refueling, and only about a third of it is actually used to replace that, whereas 2 million tons of coal come every day or so, shipped by rail from Wyoming to Wisconsin or Minnesota. Now, it's important to understand that there are 2 circuits of water. And so we're dealing here with the primary circuit, this part here, and it goes through the hot leg. So basically, this cooling water that comes in at about 290 degrees centigrade, water flows then down, as I showed you before, and up through the bottom and exits out the hot leg. This pressurizer simply maintains the pressure so that everything is going smoothly, and goes into what's called a steam generator. And we'll come to that in the next slide. But they point out that 20 tons per second of water flow goes into these and passes through 5,000 of these inverted U tubes where the primary heat is given off. And this comes back out the cold leg here at the lower right, and that eventually connects back to this crossover leg here. So that is the primary circuit. We're going to see next the secondary circuit. Oh no, I'm sorry, that'll be in the slide after that. But it does go through these primary circuits. They have 4 cooling loops here, and I'll show you a detail of this later. These are the steam generators. They could have one massive one, but it would just take up a lot of space. And they find it's using fewer loops would require larger steam generators and more pumps. A lot of this works with just pressure and not so many pumps. So it works fairly automatically, not so much need for valves or complex pipe work if they have 4 as opposed to 1. But sometimes in smaller plants, they will just have 1 or 2. But for this typical 1,000 or 1,200 megawatt plants, reactors, they use 4. Okay, here is the steam generator. This is the secondary circuit that I'm talking about. This is where the primary and the secondary circuits meet. Note the size of an individual person here, the worker size next to the hot leg that's coming in here directly from the reactor. And it goes up. This is the hot area, hot leg of entry in the, it goes up the inside of these 5,000 thin walled tubes. There's enough space between these tubes for the secondary circuit, that's this pink here, to come up and up into the, eventually out the top where it feeds into the secondary circuit, and it goes through some further production to generate electricity through the steam. So this generates the steam, then harvests the heat energy, converts it into steam at high pressure. The next slide will show us a little bit more this entire secondary circuit. So here is the steam generator with those inverted 5,000 thin walled tubes, and the steam comes up and drives these turbines. And we'll talk in more detail about the turbines. There's a moisture separator here. There's a lot of the steam gets to be, most of it gets recovered. And there are various feeders, de-aerators getting rid of the air and so on, pump feeds and so on. And it goes back into the steam generator. So this is the second circuit. The steam itself is pink, and the water is very hot water under pressure is the second secondary circuit in these things. There are two circuits quite different from the boiling water reactor where there is just one circuit. Remember I mentioned this, the pressurized water reactor is twice as popular. There are about 300 of those in the world as opposed to 150 of the boiling water reactors. Continuing on to the steam turbine, these have been reliable in use for coal plants, gas plants, and nuclear plants for 130 years. There's a lot of experience. First, they passed through fixed blades, and then moving blades, and then larger fixed blades and moving blades. And this way is to get the most rotational energy out of the steam. And then this, of course, turns an electric generator. They have at each end bearings, and they have glands to keep the steam from exiting and escaping without turning the shaft. And this is a picture of an electrical generator. We all know what generators are like. Some of us have them on our bicycles in the old days, rubbing against the bike tire and an electric motor in reverse. This picture has been used in some things to display a nuclear reactor, and it's a misnomer. These electrical generators are used for coal plants and gas plants. There's nothing special about it being a nuclear plant, except it's probably a cleaner environment. And but these components are the same. So these are two side-by-side 600 megawatt turbine generators to give about 1,200 megawatts of power from a typical plant. About a third of the heat energy, I mentioned this already, produced by the reactors turned into electricity and sent into the grid. The other 2/3 leaves the power station as waste heat. And this can be a problem, one of the negative effects of the pressurized water reactor, because in France and in Europe today, the rivers are about half as full as usual, and they have to actually turn down some of the reactors that are on rivers in the middle of the countries, because the water is low and warm, and therefore they don't want to be having the rivers much hotter, and so they've had to slow down some of the reactors. The sense of scale here, talked a little bit about this before, but this gives us an idea. A pressurized water reactor produces about, I mentioned this, 3,500 megawatts of heat, or 1,200 megawatts of electricity. This primary circuit operates at 300 degrees centigrade and 155 bar. There are a number of ways of measuring pressure. We use pounds per square inch. In Europe, they don't. They use a whole bunch of different terms, but the author here in England has used the word bar because it's an easy way to remember it. It's just an atmosphere, or equivalent to 14 psi. So 155, that's a fair amount of pressure. The water flows through the primary circuit at 20 tons per second. The reactor cooling pumps spin 1,500 times per minute, driven by 50-ton motors. All of it will operate reliably for 1 to 2 years before it needs refueling. I've been wondering why light water people are so tolerant of having to shut down every 18 months to 24 months. And they like it because it not only keeps them busy, but there are a lot of things that they can do while the plant is down. It used to take about 6 months, and now it takes about 6 weeks. But while it's down, they can not only refuel, but they can check a lot of other things. And it's like bringing your car in for a checkup every now and again to check the oil and all the other things we do when cars are checked up. And it's important to workers and authors like Colin. So now he goes to the idea of starting up your reactor. He says, after the fuel has been loaded and the control rods inserted to keep everything calm, then the reactor is still considered to be subcritical. We use in science fiction, and probably in some of those cartoons, this term critical, and it's a misnomer in science fiction. Each time the control rods are pulled out a little bit, the flux of neutron increases and then stabilizes. So each one of these little green arrows here shows the removal of some control rods, and it comes up and then it levels off because these are fairly stable reactions that are started, and just removing some control rods will increase it. But you have to do it several times before you reach what's called criticality. This is the example here. Criticality, sorry about the fuzzy spot there, happened somewhere in here. And then the reactor became supercritical. And Fermi always called it exponential, was his term. But supercritical has to be maintained for some time to raise the power about 1,000,000-fold from when it first starts out. So it doesn't mean unstable. It just means that you've got it in a rising fashion, in an exponentially increasing reaction until you want it to level off at a higher point. And you adjust the control rods when you reach 3,500 megawatts of heat for a typical reactor. Okay, what is the other thing that's so special about fission? Are there any questions here before we move on?
Richard, this is Tony.
Yes, Tony.
You mentioned in France, I believe that they're having difficulty because of the water-cooled nuclear plants heating the water locally. Yes. I think some of the fourth generation, like molten salt, doesn't even require water. Is that correct?
Absolutely. I was going to mention that later. I'll talk about that, but that is a very good point. The molten salt reactors don't have that problem at all. There are several other big advantages to the molten salt reactors. The biggest reason I think why people haven't used them is nobody's used one ever since the last one was shut down at Oak Ridge. They've not been in use for some 40 years or so. And so there isn't trained people. People like what they do. They like to stay with what they do and don't have to learn too many new things.
I think in Idaho at the university there, I believe that's the one that's under testing and construction at this point in time. Yes. As a molten salt.
Right. That's true. Yep. So it's nice to know that that's going, but we have a lot of other people. There are 440 reactors around the world, and of course not all of them are light water reactors, but majority of them are, and those ultimately will need to be converted, I think, to molten salt reactors, because they we just don't know how long they're going to be viable. Some people talk about the lifespan of a reactor as 80 years. Others talk about it going perhaps to 100 or beyond 100 years. It depends on how well the concrete holds up and how long the concrete can be, for how many more years it can be maintained. But ultimately, I think they will be changed to something that's inherently, I think, safer. It's hard to beat the safety of these, though. They are a lot of really good features about light water reactors, and we'll touch on those a bit later. But thank you, Tony. Those are good points. Any other comments?
Yeah, this is Lou. I don't know if you're hearing me, but
Hi, Lou.
I heard that in France there was some corrosion issues.
Yes.
And one, there's water issues for cooling and then corrosion, and they sort of think they have those taken care of pretty quickly.
Yeah, they have a lot of experience in France, and I think they're working on it. But what worries me much more than that is the power of the Green Party. The political problems in Germany are creeping across the border into France, and they're pressuring Macron into cutting back his nuclear fleet. And that would be a shame. The French have accomplished a great deal, and I would hate to see the Green Party get dominant. It's a political issue, though, not a technical one. But you're right. Thank you, Lou. Good point. Okay, moving on to the fission products. This is complicated. there are a lot of different fission products. When the atom splits, it doesn't split exactly in half. For some reason, it always gives two different fission products. And there's a range, and I didn't include that slide. I had it in a previous talk, but it's not critical for the point that Colin is trying to make here. He simply says it splits unequally into smaller atoms. The fission products are unstable, and they produce heat as well as the initial fission reaction from decay. So you can get heat from two sources here, fission and from decay of the fission products. And as they decay, they emit beta particles, which is simply an electron, or a gamma ray. This is much more serious. Gamma rays are very penetrating, and they can make a reactor unsafe for personnel. And they have to take good care of that. They want their workers to be quite safe, and they check them very carefully to see how much radiation they're exposed to in the workplace. So this sort of product, iodine 131 decaying to xenon, because when it loses a beta particle, that changes its valence and its proton properties so that it becomes something with the same atomic weight but a different atom. Xenon is one of the noble gases, and but it releases gamma rays and it makes the fuel rods lethally radioactive. So it's a potential problem. Now that's iodine 131. There's another iodine isotope called 135. It's got a squished in this drawing. About 6% of the fissions result in 135 iodine. And that decays also to xenon through the beta particle. And that then leaves another beta particle and converts into cesium 135, or it can capture a stray neutron. There are neutrons around at various energies inside these reactors, and it can acquire a neutron and become xenon 136. So it goes from 135 to 136 just by picking up a little blue job. Now, unfortunately for us, fortunately for us, the xenon, the iodine 135 and the xenon 135 are only last a few hours, but they will affect how you drive your reactor. And so these are important things to be aware of. And this entity is a useful one for determining the power of your reactor and how, like a tachometer in your car. It can be a useful factor. Also, oxygen 16 is also useful. There's plenty of oxygen atoms in a light water reactor, and a few of them will be hit by a fast neutron also here. And nitrogen 16 is unstable, loses a proton within seconds, but then emits a gamma ray. And the oxygen 16 gamma ray emitter also is a useful way to measure power in your reactor when you have sensors for that.
I did Sudoku.
Yes, is there a question there?
Wordle on my own on the floor. So now you have to do it on your phone. I started with ounce and got it in 4. So we're going to have a challenge.
I'm sorry, I'm not hearing that clearly. Something about an ounce. Could you repeat the question again, please?
I didn't actually have a question. Actually, I think it was Don Reeder has his unmuted. If he could mute it again, I think he was picking up background.
Thank you.
He unmuted.
Sure. Okay, so we'll move on to another fission product. One would tend to think that it would be abbreviated as PL, but that's platinum. And so they took the next letter, U, and I always help to remember it because plutonium is a dangerous atom, and all of its isotopes. So I think of it as the smelly one, and I think of PU. It helps me to remember that that's the symbol for the dangerous one. The 238, which is much commoner in uranium fuel, even when it's been enriched from 0.7% to 3%, as is often done when the reactor is first loaded, there's still a lot of uranium-238 around, and some of the neutrons will be absorbed by this and become 239. And that in turn will decay to neptunium and eventually to plutonium. That's fine in first because the plutonium actually fissions and is a nice contributor to the energy in a nuclear reactor. So, and it has a long half-life, so it's a helpful contributor. But all this reaction goes on, fast neutrons accumulate, not just slow ones, but fast ones, and that flux will harden, and some of it will leak through the reactor walls as the number of them increase. And that makes the reactor potentially more dangerous if they're around workers. And so they have to be aware of that and be more careful as the reactor goes through some time before fueling up again. You need to touch on the basis for the pressurized water reactor versus the boiling water reactor. And it's useful to know this, have some idea of this curve, temperature in the abscissa versus pressure in bars on the ordinate. So the pressure here would be 0 for, well, they have it at 0 for atmospheric, but it's 1 bar basically when they use a boiling water reactor. But as you raise the pressure, you also can increase the temperature of the steam. And so when you're up to about 155 times atmospheric pressure, you are at about 3.5 times the pressure. And those increased, you just don't get temperatures like that at 1 bar. When the water is converted to steam, that just passes off as steam, and unless it's pressurized, you cannot raise the temperature above 100 degrees. So boiling water reactors then operate at that temperature versus pressurized water reactors, which operate at about 3.5 times the pressure. And that is some good points and some not so good points, but we need to be aware of that as we think of the advantages and disadvantages of each. Moving on now to what happens when we fuel a pressurized water reactor. Well, first of all, we have to remove the lid, and that is quite involved. You have to remove 50 bolts, 500 pounds each, use a crane to lift the lid off, the head, and then you have to flood the cavity with 1,000 tons of borated water. Borated water means boric acid, basically. It's boron in the water readily absorbs any photons and makes it safe to look right down in. I don't know if any of you, I think a few of you in the audience were with us when we made a visit to the research reactor at the university. And we remember looking down into this blue cavity. We just had time to have a little peek. It's pretty spectacular to look down into the center of this, and a better view is here. All of we don't call it waste anymore, we call it slightly used nuclear fuel, or SUMFT. It's been removed from the storage pond, and they only change 1/3 of the fuel at the time, and they put it in the water storage for a while and then later in dry storage. But this allows us to shut down the reactor to maintain safety and lets us rearrange the 2/3 of the remaining fuel. That's what Colin is saying here. He says, note the blue glow. This is Cherenkov radiation, and it comes from excited electrons that are traveling faster than the speed of light in water. And so you have this unusual glow. It certainly impresses people when you see it. We saw it at the university reactor. It was about 10 years ago or so. I think.
Richard, this is Tony.
Yes.
I don't know physics. Maybe Don can help me here. I didn't think anything can go faster than the speed of light.
Well, we're talking different media. In water,
Huh.
it will.
Huh.
And it's 186,000 miles
Per second.
per second. Yeah. And it'll
Yeah.
go a little faster in water. Water is a totally different medium than air.
Sure. Yeah.
Sound will travel also more rapidly in water, I believe, than in air. And,
Interesting. Yeah.
But
I did not know that.
this is Lou. It's actually in a vacuum as well. It can travel, but you know, this is water, like Richard said. Water has different rules.
mm-hmm. Yeah. Sound, of course, will not travel in vacuum, but the light will. You bet. You're absolutely right. Thank you, Lou.
And of course, you know, the light rays that come from the sun are traveling through a vacuum.
Yep.
To get to us.
That's right.
Hmm.
But we don't hear all the racket of the nuclear explosions in the sun because it can't travel through a vacuum. Right? So only light can. And yeah, it's interesting. It's hard to think of light going faster than the speed in air, but we're so accustomed to air or a vacuum. Okay, moving on then to the boiling water reactor. This is a truncated pressurized water because there's no separation of water circuits here. You don't have a primary and a secondary circuit. And the boiling water in this reactor just goes out as steam and goes directly into the steam generators. And therefore, to do this, you don't want to have the control rods in this chamber. It would mess things up a bit, so you have to put them in from underneath. But that can be done. And I mention this because when we look at small modular reactors of the future, some of them are going to be boiling water reactors. And so it's not just the 1-to-3 relationship in the past of light water reactors. There is a future for boiling water reactors, and it's good to be aware of it. Boiling water construction costs are lower, but there is a little thing. I talked about nitrogen-16. It accumulates in the steam that goes to the turbines, and that has to be shielded. So you cannot have workers in the steam rooms, in the steam generator rooms that you saw before, because there's radioactive nitrogen in that steam. Steam, as you know, is H2O, but there's a lot of nitrogen and oxygen atoms mixed in with it in their atmosphere. So the 70 boiling water reactors that are operating are now mostly in this country and in Japan. And I think everywhere else in the world, they've using CANDU or pressurized water reactors. But it's just something to be aware of, how they differ. Then we'll talk now a little bit about the CANDU reactors. Heavy water, while it moderates neutrons effectively, it captures far fewer neutrons than light water does. And so because of that, you can use 238 for fuel. You do not have to enrich it. And that's a big plus because the enrichment process, well, it keeps the people in Iran from having bombs, which is nice. But for the rest of the world, it's costly. There are 3 different ways to enrich it. Centrifuges were used first, but there are other more efficient ways to do it, but it requires a lot of ingenuity and industrial complexity, sophistication. Canada first tried this approach back in 1962. Fuel bundles are placed horizontally in pressure tubes, and this is key. These pressure tubes are individually isolated from one another, and therefore you can push in fuel from one end. And if you have these fuel units placed in such a way that the oldest ones are placed first and you keep track of the newer ones that are coming in, you can push out the old ones as you push in the new ones, and you do not have to shut down the reactor. So there are 31 CANDUs operating successfully around the world. About a third of those are outside of Canada. And there are 13 similar designs, but not quite the same in India. India liked the idea, and they have been using them as well. Some people criticize Canada for sending CANDU reactors to India, thinking that, excuse me, that they developed nuclear bomb technology as a result of that, but there's no good evidence to confirm that, and I think it's probably a rumor. Okay, need to touch on Magnox reactors, because those were the kind that England originally had. They were commercial reactors, and they were fueled also with 238, did not require enrichment, and that's handy. So they moderate, if you use graphite as a moderator, you do not have to enrich the 238 to 235. And instead of cooling with water, they cool with pressurized carbon dioxide. As long as you don't have a leak of the CO2, that should be fine. The uranium fuel was metallic, clad in a magnesium can. And because of that cladding with magnesium, and it was non-oxidizing, they came up with the name Magnox. So you might hear about it. 26 were built in the UK, but the last one was shut down 7 years ago. So this is more of historical relevance if you want to look into the history of nuclear reactors in England, but they just basically are of historic relevance now. But that was important, of course, to Colin, and so he brought that up. Okay, get this down there. They did move then from Magnox reactors to a slightly different type. They call them advanced gas cool reactors. They also have the CO2 coolant, as Magnox did, but it has higher thermal efficiency because of the higher temperature. They operate at 600 degrees centigrade, and that forces them to use uranium oxide rather than uranium metal in steel cladding. So it does require some enrichment, which they didn't have to do before. So these AGRs, or advanced gas cool reactors, have some relationship to the earlier Magnox ones, but he points out that there is less inherent stability than water moderated pressurized water reactors and boiling water reactors. So these ideas that originally came from Oak Ridge back in the days of Wigner and Weinberg are the standard and of today. And until molten salt reactors become well established, people in our audience like Stephen Shellen has a lot of experience with pressurized water reactors, and so do all the people like him in the world today who are departing their wisdom to us as they help us through the transition. We should also touch on Russian reactors because we're hearing a lot about them in the Ukraine. RBMK is a funny word. It means high power graphite moderated in Russian. So R stands for reactor, B stands for Bolshoi, and I can't even remember what the M and K stand for, but whenever you see those letters, they are clearly of USSR origin. The fuel is embedded in the graphite the way it was originally done in Chicago, and the coolant used is light water. So they have the benefits of using water, and that water has what's called a positive void coefficient. That is, as it expands a bit, the molecules, their they push the fuel a little bit, atoms a little bit further apart, and so there's an inherent separation of molecules, and when you have that positive void coefficient, it provides inherent safety. You don't have that so much when the isotope is embedded in the graphite. And they say that this general combination of using graphite moderation and water cooling, when they're used together, they're inherently unstable, particularly at low pressure settings, and that's what led to Chernobyl. 17 of these were built over the years by the USSR, including 4 in Ukraine. And those are the ones we're still hearing about that are now being occupied by the Russian soldiers in some places. And they are a bit scary, but particularly the way the current operators are being abused. But anyway, it's something we should be aware of, and I think everybody will rest more easily when they're all shut down eventually. They are particularly unstable when working at low levels, energy levels. And in the case of Chernobyl, they did several things that were bound to lead to a disaster. They asked them to shut it down suddenly, and they made all they shut down the cooling, they shut down everything, and it just, the instability of it led to some big problems. The control rods got stuck, and they had a big problem. And there was a lid, but there was no pressurization or significant containment. And so people don't know to this day whether it was a pure hydrogen explosion or just a pressure explosion from inside, but they think that some isotope did get blown up to high levels because it was picked up some cesium was picked up in Sweden just a few days later. So it was a serious explosion, the only really serious one of the 3 accidents that people talk about. That's the only one that led to known significant mortality, and that can never be repeated because even these reactors that are in use today have significantly more containment than the one in Chernobyl. It was a one-of-a-kind accident waiting to happen. Now, the rest of these slides are a little different from, well, there are just no slides available for these things after that last one that I showed you. And so I took these images elsewhere, but he did talk about small modular reactors. He wasn't very enthused about the need for them. Colin is used to the pressurized water reactors that he's worked with for years. But he does admit that these components can be mass produced offsite. And the advantage is you can use various modules from 2 to 4 up to 12 or more at a particular site. The image showed here is from NuScale, and they have a nice way of combining those 2 water circuits in one vertical thing that can be virtually buried underground in this area, so that the steam line is just coming out here and the feed water going back in, and it's a very self-contained system that does not require electricity. It convects naturally, and its size is such that you can use this natural steam convection without pumps and requiring electricity. The NRC likes this of all of the small modular reactors because it's a water moderator, and we're also used to it. And so it is going through the process fairly well, step by step. It requires a lot of steps, but so far so good. But in case you think that it's only NuScale, let me point out to you that there are a lot of small modular reactors in the world. This list here are various small modular reactors that are in existence and operating today. Pakistan, China, India, Siberia. This one, I showed you pictures of this one. It's a floating reactor, and they have 2 35 megawatt reactors. This is pressurized water. And that's been operating for a couple of years now. This one too, and in China. So these are all operating, and we talk about it as though it's something in the future. Well, it is in this country. Yeah, these small reactors that are under construction already are in Argentina, China, and Russia. And it's only when we work our way down to new scale here that we see what we just saw on the last slide, something that is expected to be starting up in about 7 years or so. And so we're really way behind the rest of the world. South Korea has one plan, Voltec in the United States. I'm going to show you a couple of pictures of this one because it's a boiling water reactor, but it's made by GE combined with Hitachi, and they're hoping to have it running in about 6 years. And so here's Natrium, Bill Gates' reactor. Terrestrial energy in Canada with an integral molten salt reactor. Sorry about that interruption, it'll stop momentarily. Very nice system in Denmark, and so on. So there are all kinds of them in progress. Moltex getting very involved. So this is a molten salt reactor. So these are on the way. They're going to transform nuclear energy in the future. But I thought it was kind of interesting that was getting quite a bit of comment here. I think they think GE has a lot of experience, and they think they can get their costs down with the simplicity. And this is an example of their reactor. Of course, it's an artist rendering, but the inside of it, they reveal here this, not too different from NuScale, but not quite as condensed and as compressed. And that's sort of semi-buried. And these are presumably at ground level. So here are the steam generators here in the various offices and perhaps sleeping accommodation for people. I'm not sure if these are beds or not, but anyway, it's some detail of the boiling water reactor called the, I think I misspelled that one. I think that should be a W, I apologize. Okay, coming now, these last few slides here. If you haven't guessed it from the latest bills that are passing in Congress, DC, Washington has finally caught on. And so my title of this slide is, why is fission finally favored? I think people are recognizing that this is durable energy, not just 20-year replacements. People are starting to think about the fact that these last for 60 to 80 and possibly more years. It's also becoming more evident the energy density is catching on. People fuss about waste, but I think they realize that it's not really waste, but slightly used fuel, and it's far less of it than with other sources like coal. There's less use of rare metals, and the cost can be contained by small modular technology. I rather like this image called the lowest physical footprint, and it compares coal and gas, where you have the blue here is shown by the area required to produce 1 billion kilowatt hours per year, and 4 to 8 miles here for gas, whereas 1 mile square for nuclear. And then you look at this yellowish box, 4 grams of CO2 per kilowatt hour, huge amounts of CO2, a tiny amount here, presumably relating not to the emission of operation, but of construction. You're going to lose some, emit some CO2 when you're pouring the concrete. Wind and solar and hydro, significantly more grams of CO2 emitted in considerably more space. So it really is, finally people are waking up to this. I just got a slide from Alex Canara yesterday that shows it awfully well. He says it's time to compare the materials of solar, hydro, wind, geothermal, and nuclear. And I thought this was interesting because they include water. Most of the time we don't include water. We talk about the steel, concrete, glass, and cement for these various things. A lot of cement for wind to bury the base of them so they stand up and don't fall over in a high wind. But when you compare it in terms of unit of source of electricity, nuclear is tiny and even far less than solar. So it's something that we need to be aware of, and I think that it helps to explain as a little addendum after Colin's talk, where he didn't go into these things in much detail, why Washington is becoming, if they dare to mention the word, a little more positive about it. And some final conclusions. Marie Curie said, "Nothing in life is to be feared, only understood. Now is the time to understand more so that we might fear less." And James Hansen made a famous statement, "Nuclear power paves the only viable path forward on climate change." So with that, I will end my slides and open things up to comments and discussion. Let me stop the share. So we're back to a group again. Yes, I see a hand up from Don Reeder. Thank you, Don.
Yes, I would like to inquire about thorium. Is anything going on?
That's a good question, Don. Yes, the Thorium Energy Alliance is meeting in New Mexico next week, and they have quite an active program. But that doesn't quite answer your question. I think that probably the only significant avenue for thorium will be through the medium of the molten salt reactors. And we're waiting for that to go. And when you look at the history of molten salt reactors, where people have been expressed an interest in it, they start off with an interest in thorium, and then they switch to uranium. I think it's an easier fuel to have. It's more readily available, perhaps less expensive. I don't know why it should be less expensive. There's 4 times more thorium around than there is uranium, but it seems to work out. But I like the idea of thorium. I share with you, if you're looking for an update on it, if you go on rethinkingnuclear.org and look under the news section, there's a good article that's been linked there about thorium, and I recommend it to you, anybody who wants to learn more about thorium. But I think it's quite a ways off in the future. I think it's got great potential, but I don't see it happening anytime very soon. I think it's going to wait for the molten salt reactor to become popular, and then we're going to have to wait for a new breed of graduate students and engineers to come on board with an interest in thorium. I think I would estimate that's going to take another 10 years or more. Any comments?
I got a question. What is the difference between molten salt and thorium? I mean,
well, they're very different. They're very different. One is a fuel and the other is a machine. So the molten salt reactor is the best way to use thorium as a fuel.
So it's mixed into the molten salt?
Yes, that's correct. You have the thorium instead of uranium as a fluoride. Usually it's a fluoride. Sometimes you can use chloride, but yeah, it's the beauty of the molten salt is. Let me just read a couple of thoughts that came across this morning in a comment about Moltex. They say that by replacing water for cooling, it can operate at atmospheric pressure, which is rather nice. You don't have to have so much pressurized piping and worry about leaks. The other, of course, advantage of the molten salt is that you do have a leak, and it comes out of a pipe, it solidifies because these salts, as soon as they cool off a little bit in atmospheric air, they become a solid. Plus, they have automated waste tanks, so that if there's ever a pressure loss, not that there's a pressure in the first place, if there's ever any leak, you can just hit a button and everything goes into the containment, an open facility in the basement that's ready to harvest the fluid. So there's a lot of fail-safe. So it avoids the potential loss of cooling and hydrogen accumulation and explosion. It's far, far safer in the long run. Also, it can respond to changes in energy demand, which makes it really nice. One of the problems that I didn't talk about much here is that it doesn't load, these pressurized water reactors really take a lot of moving up and down into supercriticality and subcriticality. They can't instantly follow when the sun goes down or when the wind stops blowing. They really can't. And nuclear takes a lot of blame for this. Before we had all this solar and wind on the grid, nobody minded that nuclear was low and steady for all this time. But they almost blame nuclear for not being able to load follow once we had all this intermittent energy pouring into the grid. And finally, they say that these molten salt reactors will operate for 60 years, and they only need 2 short breaks for refueling. So as opposed to the breaking now every year and a half, we're talking about every 20 years. And then you don't have to, throw out your fuel, you just do a bit of refueling. So it's a lot of huge advantages to molten salt. But thorium is simply an alternate fuel. You can use uranium in the molten salt.
Yeah, they both work. But, this concentrated solar power facility where they had all these mirrors melting molten salt on a high tower, the reason they failed was they couldn't control the molten salt. And maybe that technology has been solved. That would be great, because there's probably corrosive issues or something like that were tied to the molten salt. But there are only 2 facilities built, and they are both done. I don't think they've ever revived them. Maybe for other reasons than just the poor molten salt management. But the one thing at Argonne that was pounded in our heads for decades was you take a corrosive reactive material and you put radioactive materials with it. That's a mixed waste. That's a bad karma. They just pounded that in our heads for years. And I don't know how, if you do get a leak or how you deal with that waste. I don't know. And I need to learn a lot more. I admit I didn't go to the website, and I will check out these reactors.
Well, let me just tell you briefly, Lou, that there is what's called a frozen plug at the bottom of every molten salt reactor that's ever been used that I'm aware of. That frozen plug will melt if power is lost, because the freezing is maintained by a refrigerant. And just like you've got a freezer in your refrigerator that freezes ice cubes, if that power is shot, the ice cubes rapidly melt, the plug rapidly melts, and all of the fluid just drops down into a big containment area that below with gravity. So it's a gravity-fed freeze plug. And I think that provides the safety that you need.
But you still got to process that material. It's a hard material to deal with, I think. But hopefully that won't happen. But it's dealable. I'm sure you can sequester it and cap it off or do something with it.
It'll be a solid. It'll turn to a solid as soon as it cools down.
Yeah.
Because you're talking something that's 800 degrees, not just 100 or 300. And this also is a highly efficient system for converting to electricity. So it has a lot of really good features, but it
I was aware of that dump tank. That dump tank is great, whatever you want to call it, but and it's passive, which is great.
Indeed.
Richard?
It's done reading.
Yeah, it should also be mentioned that we had a molten salt reactor operating for 22,000 hours at Oak Ridge back in the 60s. And when they wanted to shut it down, they just pulled off, they just disconnected it from the grid. It had no power supply. Exactly what happened at Fukushima. And what happened is nothing. The frozen plug of fuel melted, drained into a tank, and it's still there, sitting there in Oak Ridge. It's been said that that could be reactivated if you wanted to spend the money. So it's not something that's never been done.
Yeah.
They didn't use it to generate electricity. It was what you would consider a research reactor.
Yes.
I got a couple other questions, Richard. Do you want them now?
Sure.
Okay. Well, first of all, is this presentation going to be available to download?
Yes.
Yes, it will be on YouTube probably later today. And then the editing of some of the preliminary discussion will be done by Stephanie over the next week or so. But it goes up automatically, even though she's in Florida in a library at the moment. These go up, and you can find it at PLATO Madison, all one word, platomadison.org. And then when you come up with the website, go to recorded sessions. And when you go to recorded sessions, then you go to lectures, and they're listed in reverse chronology. So the most recent ones are seen first. We share, they're not all this group. There's another group, something like current events, but I've forgotten the name of the other group. Oh, Whither the State, I think it's called. And so you'll see we alternate with Whither the State, and you just scroll down to find earlier ones. It goes all the way back a year and a half to when Meredith Engwin talked about the grid. And
Okay.
we're all still there.
All right. I have a question on talking about waste heat, and the image showed, and you stated that there was about 2/3 was waste heat.
Yes.
Was that with a boiling water reactor or a pressurized, or is there a difference?
Both give you a lot of waste heat. And
Okay.
It has to do, people don't talk about it, but with coal or with gas, you have these, with gas, you have these combined generation plants. We saw one on a field trip some years ago where they were trying to harvest some of the mechanical energy from a gas plant in two ways and making it more efficient. But basically, any gas plant or coal plant has to generate steam, and they go through the same sort of thing. And the laws of thermodynamics, as I'm told, pretty much limit you to about a 33% conversion of heat energy to electricity.
Okay, that was my next question. So in effect, regardless of the heat source, you're going to have approximately that amount of waste heat.
Yes.
Okay. Then I wanted to mention something that maybe some of the people don't know. Most of our computers have a clipping tool, and when these programs are on, if you use that clipping tool, you can quickly capture what's on the screen. If you want this particular image, it's easy to do right while the presentation is going on.
It's a great tool. Shift Command 3. If you hit the Shift button on your computer, the Command button, and in the number 3, you will take what's called a screenshot. I think that's what you're referring to, George?
It's similar.
Yeah, it's great. It's a wonderful way. I use it all the time. I don't know how many screenshots I've used, and then I put them through Photoshop sometimes to get rid of what I don't want to see in the picture. But it's a great way to harvest images in your computer for a later talk. And you're a great talk provider, George. I have to congratulate you for your efforts to communicate effectively to people who are on the wrong wavelengths.
Now my final one harks back to your first image. Is it easy for you to put that up or not? I don't have to have it.
Oh, do you want me to send it to you?
No, I want to
yeah,
look at it.
you can take a screenshot. Do you want me to put it up now?
Yeah, because I want to ask a question about it.
Okay, sure. Let me get the screen share. And we're on the last slide, so let me, well, I guess we can do it from there. And what I'll do is I'll go in reverse sequence. Pardon the flashes. I'm gonna have to flash through a bunch of slides, but they're not that many. There you have it.
Oh, it must have been, go to the next one.
Okay. This fellow here, the author.
Next one.
Okay. That's the
so-
joke. A
sorry.
man and his dog.
Well, maybe I'll do, I must be wrong on the location of it. There we are.
That's a good one, yeah.
Near the bottom, it says in total, they produce 1/7 of the world's electricity and a quarter of its clean electricity. That word always worries me because people have a different idea of what clean means.
Yes.
And I wish they would define how they're using it.
Right.
To my point, in my opinion, nuclear power is the cleanest because of its high efficiency and its low use of materials per kilowatt hour generated. But some people think that anything that other than coal or carbon is clean, and they're not all equal. And
Right.
I think we have to do our best to make that apparent.
Sure, you're absolutely right. I think I put in the word clean there because I was running out of space. And so rather than say carbon CO2 free, I just put in the word clean, but I put it in capitals.
Put it in quotes.
Yeah, it's not a quote, and you could easily say CO2 free. Yeah.
No, I meant put the word clean in quotes.
Right.
Whatever.
Yeah,
Thank you. You're very
very
helpful program.
Make you feel better. Oh, I tried to do it, but I promised to put it in quotes.
Yeah.
Okay,
Thank you a lot.
I'll do that.
Can I say one thing about waste heat, Richard? That a lot of industrial processes need this heat to run. It's going to be part of my talk in 2 weeks.
Yes.
And that's not going to be wasted. It could be readily used, and
Oh yeah.
probably would be one of the best ways to keep nuclear thriving. Is that materials production.
Yes, you can use it for steel production. We're using coal now. Now, coal does provide a lot of carbon, which you need for steel production, for mild steels. But
That's true.
So you're going to need some coal for that, or some other carbon source. But you're absolutely right. For distilled water, for example, in parched deserts, you can use that heat beautifully for that.
Mm-hmm.
So I don't know if you know the history of that, but Weinberg at Oak Ridge offered to the Prime Minister of Israel a distilled water production plant powered by nuclear energy. And the president of Israel at the time said, "Are you crazy? Why would you want to put a nuclear plant here in this hostile environment where there's so many terrorists around?" And Weinberg replied, "You had a lot of chutzpah to put a country in the middle of the Middle East. So why? So you're accusing me of having a lot of chutzpah." I thought that was a great line from Weinberg. Also, Weinberg then turned and offered it to Los Angeles. And this was a long time ago. Weinberg has been gone now for quite a few years. But whoever was running Los Angeles at the time said, no thanks. I think today they would love to have a nice modern reactor with all
For
that.
sure. Absolutely. Well, and the other thing too is these SMRs, if they're smaller, corporations may invest in them. I mean, it puts the heat and the power all together in a spot where they can use it. Primarily like in the Houston area, there's so much chemical synthesis going on down there. They should have some of these in that area.
Yeah, my biggest concern is the politics more than the reality of nuclear. When I see the power of the Green Party in Germany, in France, and in California, and the refusal to acknowledge nuclear's role, that really worries me. It's embedded in their psyche so deeply that it just seems you can't talk to them. And then you get people like Edwin Lyman of the Union of Concerned Scientists. Edwin is often interviewed, and recently he was interviewed on PBS, and he did a wonderful job. They were asking him about the risk factors in the Ukraine, and everything he said was right on. And so the guy is very knowledgeable, but he has got a fixation on safety to the extreme. And I think sometimes he exaggerates the dangers to the point of making them safe. And sometimes it can feed into the Green Party and make them feel all the stronger. So you have all this political exchange, which I think really harms nuclear when you see the potential here. But my goal in talking today was to just help us to see the point of view of a good teacher with a familiarity with the light water reactor and his ability to convey enough of the intricacies of the pressurized water reactor, the boiling water reactor, and how safely they can be run, that I thought it was refreshing. And I plan to give the same talk in 2 days to the Global Affairs Group. I don't know if it will go as well with them as it is with you people, but I'm hoping that they will see the point of view too.
Richard?
Yes.
It's interesting to note that as of the latest count, 20 other nations in the world are expanding or have approved expansion of nuclear power. But in the United States, we got to fight to keep what we have. And that's just outrageous.
Yeah.
People don't understand how powerful the green organizations are.
Yeah.
And I think one of the most telling examples for me was Bill McKibben. His book, The End of Nature, turned me on to climate change. He was one of my few heroes. But at a recent, 2 years ago, Vermont rally of his 350.org, a reporter asked him, I know you are in favor of nuclear power. Why don't you come out and say so publicly? And he said, because if I do, I would lose half of my membership. That is tragic. Just think where his allegiance has gone from the environment to his organization and the finances. And that's typical.
Yeah, I completely agree. At least James Hansen didn't have such a following, and he was true to his beliefs. And so we have a strong supporter in James Hansen, and he has far more credibility as a climatologist than Bill McClyman. So I just ignore him and think of James Hansen as our hero. Yes, Don Reeder.
Yeah, just a question. I think there's an opportunity to advance the inclusion of nuclear by keeping it as an upgrade to the coal systems, because the generators and everything that uses steam is the same.
Yes.
Why can't you just replace the source of steam And then you would save all the money of connecting it to the grid and everything else.
Absolutely. There's a powerful movement today called C2N, stands for coal to nuclear, doing with just what you say, Don. Absolutely. There's a big movement afoot to do that. Any comments, Stephen? You agree with that?
Richard, this is Steve Shellen.
Yes.
I've been quiet this whole time. I think it was an excellent presentation, and kind of to address Don's issue, you can build a coal plant almost anywhere relative to the population. The stigma of nuclear power is that you must isolate it from people because it's so dangerous, and that myth has never been broken.
Yeah, I think that I'm hoping that the Nuclear Regulatory Commission will cooperate with NuScale in particular, because it's perhaps the first one, but perhaps also with GE Hitachi. These are two small modular reactors in the wings, and I'm hoping and thinking that they will allow these plants to be put relatively close to cities. I just drove by the coal plant. It's called the Columbia Coal Plant up on the Wisconsin River near Portage, Wisconsin yesterday. And it's within sight of the town of Portage, but it's nowhere near downtown. And I think that would be a classic example of where you could put a bunch of small modular reactors combined, just as Brent Ridge is doing in La Crosse. That would be a great place to put a good-sized small modular reactor that could be almost the size of a major coal plant like the one in Columbia. People are talking about taking down that plant, but what I fear is that they'll replace it with a gas plant, and what they should replace it with is either a NuScale or a GE Hitachi model. That would be great. So I think if the NRC will cooperate with these applications, they should allow plants not right in the heart of a town, but even the coal plants, as I mentioned, like Columbia, they're not right in the heart of Portage. They're a distance away. And I don't see why anybody at the NRC should complain of a small modular reactor there. But I agree with you. You wouldn't want to put a big pressurized water reactor there.
Well, again, there is no reason not to.
No, that's true.
Switzerland has for decades had a reactor in the middle of an island in the middle of a river in the middle of a town.
Yeah,
that's been operating safely for decades.
So has France. France has got reactors a block or two from schools. I mean, they get over it. They just, how did they do that? How did they get the public to accept all that?
I heard Weinberg gave me a comment about that, not personally, but in his some of his writings. He said the French believe that they discovered radioactivity, which is close enough, and of course Marie Curie did, which is close enough to fission, that the French believe that they discovered it all in the first place, so the population doesn't have as much fear. It's sort of like what Marie Curie said in my last slide.
Richard?
Yes.
I'm new to your class and I'm enjoying it tremendously. And trying to play catch up with some pretty intelligent conversation going on. I'm remembering way back when the nuclear power plant closed outside of Milwaukee, and then they had to deal with the spent fuel. And can you talk a little bit about that? You know, what reactors last for 40 years or so, and then what happens?
I might pass, if you don't mind, Jean, to Stephen, because he's probably far more aware of that plant and what happened to it. Stephen, would you like to reply or comment?
I think what you're talking about is the Kiwani nuclear plant.
Yes.
Kiwani nuclear plant is located near Kiwani, Wisconsin. It's 5 miles north of the Point Beach nuclear plant, which is located just north of two rivers. Both of those plants are Westinghouse pressurized water reactors, and they produce roughly 670 megawatts electric. They both were built in the 60s. Point Beach Unit 1 first, Unit 2 second, Kiwani third. Wisconsin Electric owned Point Beach. Wisconsin Public Service owned Kiwani. As things have changed, both of those plants have been sold. Point Beach was sold to Florida Power and Light, now known as Next Era Energy. Kiwani was sold to Dominion, which is Virginia Power. When Point Beach was sold, Wisconsin Electric created or demanded or negotiated a power purchase contract and has the right to buy the power at certain rates from Point Beach, 2 units. Dominion, for some reason, I don't know whether it was Wisconsin Public Service or Dominion itself, was put in the position as a result of the sale to sell its electricity at market rates, which are determined by auction, day by day, hour by hour, minute by minute. And then natural gas prices dropped to the bottom, and Point Beach still had commercial power contract, and it continued to provide power to Wisconsin Electric. It remained profitable. Kiwani now was trying to sell power at a rate above that of the market, and it decided that instead of trying to fight the avalanche of cash being lost, they would simply shut it down and decommission it. Every nuclear plant has a large decommissioning fund in the multi-millions or billions of dollars. And in the decommissioning, besides that money being used for taking the plant apart and disposing of everything environmentally, the company, the power plant owner or subsequent company, gets to make a profit. So they're assured of a profit to decommission Kiwani. Kiwani had recently, in 2005, gotten a license extension to go from 40 years to 60 years. Point Beach had also, prior to that, gotten an extension for both of its units from 40 to 60 years, and is now going for 60 to 80 years.
Could I interrupt you for a moment?
Sure.
Stephen, you're doing a great job, but I was wondering if you could address Jean's question. She gives us the impression that there was a problem with some of the residual material. Is that correct, Jean? What was your concern about residual material in the Kiwani plant?
I recall years ago some talk about transporting that nuclear waste cross country to a desert in, I don't know, Arizona or someplace, or California. Mm-hmm. Yeah, and that is my question. What happens to that spent pool if the plant is closed down completely?
When the plant shuts down, nuclear fuel is put in water storage for a period of time, a couple of years. and then it's put in a steel cask surrounded by concrete and set on a concrete pad on the site. There are some radioactive materials that are disposed of through certain environmental required tracks, and some of those materials may be transported because they're low-level waste. They're not active fuel, not reusable fuel. Those are transported to various sites around the country, some of which are in New Mexico, Arizona.
But the vast majority of that spent fuel, what you're saying, if I interpret you correctly, Stephen, the vast majority of that unspent fuel is still stored in those dry casks. Is that right?
It's stored in a dry cask. I don't know if there are any left in the Kiwani spent fuel pool or not at this point. I would think it's been enough years that they're all in casks.
Yes.
Yeah, if you drive by the Kiwani site, you can still see most of the plant buildings, but you really can't see where the fuel's stored.
Okay. And as I understand it, this is typical. I'll be right with you, Tony. This is typical of most of the reactors around the country that have been decommissioned. Those casks are in place and will be in place for the foreseeable future until such time as Yucca Mountain or some other place is opened, or they become significant sources of fuel for Generation 4 reactors. Would you agree with that?
That's the thought going forward at this moment. Yucca Mountain could take them right away if Colorado didn't have a barrier to it.
Right.
But most of it is valuable enough that you would want to reprocess it like it is done in Europe.
Right.
We just have a ban on that, so we're stuck burning 10 or 12% of the available energy, and then we set it aside.
Okay. Thank you, Stephen. Tony, you have a question. Yeah, I'd like to speak.
Yeah, maybe also regarding to Gene's comment or question, the spent fuel of nuclear material that's sitting in those casks right next to all the nuclear reactors around the world has only been used a few percentage points of the actual power available to us. And with fourth generation molten salt, the potential of using those spent fuels and reprocessing it on site, if the plant was built at those particular locations to replace the existing plants, you'd get another 60–80% of the fuel processed out of it, of which, like I say, well, right now it's under 5% that's been utilized so far. And the potential of using it, more of it in some point in time in the future, I would suggest the greatest potential for the future for energy. Next to fusion power, if they ever get that developed.
Right. Yeah, we don't even have to mine it. It's sitting right there ready for us.
Europe and Japan reprocess right now.
I would like to point out that the CANDU reactor not only does not require refueling, it burns up much more than 10% of the fuel.
That's what I thought too. And I asked Neil, I'm going to have to ask him again, because I asked him during one of his talks and he did not give me that impression. But that was also my impression, Don, that the CANDUs will burn up more than 2%. So we'll have to put that question to Neil again in a few weeks when he speaks.
Richard?
No, cut you off. Don, I was just agreeing with you. It's a very interesting point.
Richard?
Yes.
I think it's interesting to realize we did for a while recycle our used fuel. In the Carter administration, and prior to that, they were doing recycling. But Carter, to appease the Russians' fear that we'd be using the plutonium for weapons, agreed to stop the recycling program.
Yeah.
West Valley, New York was where Point Beach Fuel was at that time. We had to repackage it and bring it back to Wisconsin and put it in our spent fuel pool.
Yeah. Yeah, Carter had some bad experience in Canada. He was asked when he worked for Rickover to go to Canada to clean up a spill, and that didn't give him a very positive view of nuclear energy. He made a few less than ideal decisions, I think, during his presidency. That was certainly one of them. Any other thoughts? I didn't mean to cut you off, Don. Were you going to say anything more, Don Reeder?
No, I think that there is an opportunity to repackage the spent fuel rods as a quasi-recycle to use up more percentage of the fuel that exists.
Mhm.
And I don't think that's been, well, the problem is that the economy is way too important, overriding safety and feasibility and climate change.
Yeah, that's a good point. I think that the spent fuel could be used very nicely as uranium fluoride in molten salt reactors. Be a great solution for it. I don't know if there are any contraindications to that, or whether Neil would have the knowledge to answer that question, but that strikes me as a wonderful way to use the material without having to do any further refining.
I've got a question. When this spent fuel sits, it's hot and then it cools. How much of it is actually lost? How much of the energy is lost over 20 or 30 years or whatever? Is it a real tiny percentage? Does anybody know?
It's a small percentage because it's just based on the radioactive decay. There's no consumption.
There are two radiation decline curves, Lou, based upon whether you're thinking about the original fuel, which is a long-lived collection of uranium isotopes, mostly 235 and 238, but mostly 238. These are long-lived, and as long as there's significant amount of 238 around, that's going to have a very long radioactive life. The fission products, however, that are
Created.
generating a lot of heat, those generally last for about, the half-life is something in between 600 and 800 years. So when people talking about these things, the dangers of them, the benefit of bringing in molten salt reactors over light water reactors that we're thinking of in the immediate future, the molten salt reactors would fission all or most of those long-lived nuclides, particularly the uranium-238, so that you'd be left with, for storage, the fission products, which have half-lives much shorter. Instead of thousands of years, only a few hundred years. And that would represent less of a danger for eventual deposition in a proper waste site. So it's another reason to, rather than the fact that we don't have to mine any more uranium, if we could use this stored uranium in a molten salt reactor, we wouldn't have to, when we eventually bury it, after all that energy that's left in it is used, we still have the fission products will decay in a much shorter period of time. Double benefit.
I might be wrong on this, but it seems to me that U-238 and various other isotopes that have really long half-lives are not the concern. Because they emit so slowly, I don't see the hazard. I would worry much more about short elements with short half-lives that are really cooking.
Yeah.
And I think the public needs to understand that just because that element has, or isotope has a long half-life, doesn't mean it's more dangerous. But I think they do. At one of my presentations, I saw a woman get practically hysterical talking about plutonium, which presented very little risk.
Yeah, that's true. Good point, George. Thank you for making that.
I've got one point I'd like to make. We're talking about a lot of change in the types, sizes, and modes of operation of new nuclear plants. And most of, if not all of the types of designs that we're talking about were available to us in the 1940s at the end of World War II.
Yeah.
The reason that we have the nuclear plants that we have around the world right now is that the end product of all of the development was to create weapons to keep the Cold War at a standstill.
Yeah.
And therefore, all these things that we're talking about, you can go back to, say, Oak Ridge, and you'll find there's a demonstration plant somewhere that was created for that. So it's good that, number one, hopefully, despite Putin, the Cold War has gotten to the point where many nations have the ability to study all of these designs and create some innovative use of nuclear power, which is the densest, greatest energy source that we have outside of the sun. And I'll stop there.
Okay. Very good point, Stephen. I appreciate all of your input. Before we close, I'd just like to make one reminder that Lou will be our speaker in 2 weeks' time on October the 17th. And Lou, are you comfortable with this way of doing it rather than the lecture format? Do you like this okay?
Oh, yeah. If I could control it the way you have. I don't tend to go back and forth with slides if I can help it. Okay. But we should have quite a similar experience. I don't have that many slides.
Good. Excellent. Yeah. All right.
What I may do is send you a couple links if people want to read ahead, just to get a little familiarity.
That'd be good.
Just a few things, not much, not what I did last spring. It won't be that deep.
I'd be glad to send those out. Thank you, Lou.
Yeah, okay.
So just a reminder, everybody, it's 2 weeks from today online and 1 week from today, the field trip to the Holy Wisdom Monastery, and you all have that. If I have any further updates from Mark Hansen, other than just confirming that he'll be there, I'll pass them along to you as well. So have a wonderful week, guys. It's beautiful early autumn weather, and we'll see you either in a week on a field trip or in 2 weeks with Lou. Thank you all.
Bye-bye. Great job, Richard.
Bye-bye.